Hello everyone, my name is William and my partner's name is Abeer. We are doing Project 9B and our research title is A Qualitative Study of CNN Optimizers with Weight Decay. In this project, we will be comparing the loss landscape with different optimizers and varying amounts of weight decay. We are using a dataset called human faces and it comprises of 10,000 images of human faces split into two categories, 5,000 real human face images and 5,000 AI generated face images. We then use this dataset to train a CNN. Since last week, we have changed the way we have trained a model. We used to train and test the model with the same dataset, so there was a 0% margin of error. Now, we are using a 3-to-1 train to test ratio, where our testing dataset, used for tests and graphing, is not used during training. This makes it so we can gain a better understanding of our model's performance. We have also expanded our research and code to more optimizers. This week, we have integrated 7 more optimizers: SGD, Momentum, Adagrad, Adadelta, RMS Prop, Adamax, and NADM, in addition to the Adam optimizer to see how weight decay impacts their performance as well. All models were trained with 15 epoch, a batch size of 256, and a learning rate of 0.01, with weight decay set at 0.01 as well. The optimizers were tested in both weight decay and non-weight decay configurations, and our preliminary findings suggest weight decay can improve most optimizers' performances, but can also slightly hurt accuracy with other optimizers.
So the SGD performs parameter updates per training example with slow oscillatory convergence, while SGD momentum enhances this by accelerating similar directions and dampening oscillations. Adagrad adapts learning rates but faces a vanishing rate issue addressed by Adadelta and RMS prop through limited gradient accumulation. Adam and NADM incorporate adaptive learning and momentum, with NADM adding a look-ahead capability from Nestrov's accelerated gradient. Adamax retains Adam's moving average of gradients but replaces it with an element-wise maximum that tracks the largest recent gradient. So to analyze and study our results, we continued with our 1D linear interpolation approach, but we have also started coding a 2D contour plot approach, which visualizes the 3D surface, which is a loss function over 2 parameters, by projecting it onto a 2D plane using contour lines or filled regions that connect the points of equal value. So they essentially look like topographic maps that you would use to visualize the elevation levels of mountains in certain places. And the x-axis in our 2D contour plot is the alpha and the y-axis is beta. And once we have these two ways of visualizing the optimizer's approach across a landscape, we need to interpolate our findings. So the main things to consider is the sharpness and steepness of the local minima, which is the gradient of the sides, and the width of the local minima, which is the flatness. Or in other words, how much area does the optimizer have to explore? As we are also studying weight decay, the effect of weight decay on generalization performance is an important factor as well. Thank you.